Welcome to another deep dive.
Hey there.
Today we're really getting into the core of Python, what makes it tick.
hmm
We're exploring its built-in data types, the absolute basics, the fundamental ingredients for how Python sees and works with information.
Yeah, the building blocks. You can't really build anything solid without understanding them.
Exactly. So our mission today is pretty straightforward. We want to unpack these core ideas, make them really accessible, insightful for you, because if
Mhm.
you grasp these data types, you're basically learning Python's own language, how it understands everything you give it.
And it's not just, academic. These aren't just terms to memorize.
No.
They're fundamental. They affect everything.
Yeah.
Simple sums, complex algorithms.
Yeah.
It all comes down to how data is represented.
Right. Efficiency, clarity.
Exactly. The type you choose really matters for how your code works, how readable it is, how robust it is.
That adaptability, that foundation.
Yeah.
That's what we're diving into.
Yeah.
Okay, let's unpack this then. Let's get into the nuts and bolts of how Python handles information. The foundation. Numbers and truth, numeric and Boolean types. So, where to start? Maybe with the most familiar things, numbers.
Sounds good. Everyone gets numbers.
We use them constantly. But Python, it has a particularly neat way of handling different kinds of numbers, doesn't it?
It does. First up, you've got ints, integers.
Okay, whole numbers.
Right, your basic whole numbers,
Yeah.
positive, negative, like
Yeah.
x10 or y gets 500. Simple enough.
Yep.
But here's the cool Python twist. Arbitrary precision.
Okay, what does that mean exactly?
Well, in many languages, integers have a fixed size limit. If a number gets too big, you get an error, an overflow. That's annoying.
Right, I've hit that before.
Yeah. Python just handles, you can have incredibly massive numbers, way beyond what standard fixed size integers could manage. Think astronomy calculations or national debt figures.
Wow, okay.
Python just scales up, no overflow worries for standard integers. It's subtle, but really powerful, makes numerical work much more robust.
That is a huge advantage, saves a lot of headaches.
Yeah.
Okay, so int gives us precision for whole numbers. What about the numbers between them? Decimals.
That's where float comes in, floating point numbers.
Right.
These are your numbers with a decimal point.
Mm.
Absolutely vital for precision when you're dealing with measurements, science, finance.
Well,
Exactly.
Yeah.
Pi equals 3.14159, or maybe a
Mhm.
temperature it can give us 4.5. The decimal point tells Python, okay, handle this differently, allow for fractions.
got it.
And then it gets even more interesting for certain fields. Python also has complex numbers built in.
Complex numbers,
Yeah.
like with imaginary parts.
Yep, the A plus BJ format. The
Yeah.
source gives Z plus 3J as an example. So a real part 2 and an imaginary part 3J.
Okay, that's pretty specialized.
It is. You wouldn't use them every day unless you're maybe in electrical engineering,
Mhm.
signal processing, quantum physics, fields like that.
But it's impressive that Python supports it natively.
Definitely. Shows its scientific computing roots.
So Python's got us covered for counting, measuring, even modeling complex physics. But what about something even more basic, like yes or no, true or false?
Ah, you're leading perfectly into the Boolean type. Bool.
Right.
And this is arguably one of the most fundamental types because it represents truth itself.
Right.
Just true or false. That's it.
So is active true, like in the source example?
Exactly. Simple, but absolutely critical. All program logic, all decision-making hinges on the
Conditional statements, loops.
precisely. Anytime the code asks, is this condition met, or should I continue looping?
Okay.
It's using Booleans, implicitly or explicitly. It's fascinating how these two simple values, true and false, underpin almost all computational logic. They let programs react and adapt. 2, handling collections and sequences. Order matters, sequence types.
Okay, so we've handled single values, numbers, truth, but data rarely comes alone, right? We usually need to group things,
Yeah.
collections.
Exactly. And that's where sequence types come into play.
Mm.
These are collections where the order of items is important. It matters what comes first, second, third.
Order matters. Got it. What's the first one?
Well, the one you probably use constantly without even thinking about its type. CTR,
Yeah.
strings.
Text.
Yep, sequences characters. All the text you read, write, process. It's strings. The source mentions you can use single quotes, double quotes.
Or triple quotes for longer stuff.
Right, for multi-line strings. Examples like name, Alice, or message, hello world. It's how Python lets us work with human language.
It really is the backbone of communication and code, isn't it? Websites, messages, documents, all strings underneath.
Fundamentally, yes. Now, moving beyond just text characters, we get to lists.
Okay, lists. I use these a lot.
They're super versatile, defined by square brackets. They're ordered sequences, and here's a key feature. They're changeable, mutable.
Meaning you can alter them after creation?
Exactly. Add items, remove items, change items. And another big plus, they're flexible. Lists can hold items of different data types altogether.
Ah, right, like the example, my list equals 1, Apple, 3.14, an int, a string, and a float in one list.
Precisely. That makes them incredibly useful for grouping related but varied pieces of info that might need updating.
Okay, so lists are ordered and changeable. What else is in this sequence category?
Next up, tuples. Pronounced tuple or tuple, depending on who you ask.
Oh, okay. Tuples.
They're also ordered collections defined with parentheses, so similar to lists in that way. But here's the big difference. Tuples are unchangeable, immutable.
Immutable. Can't be altered once created.
Correct. Once you define my tuple equals 10, banana, true, that's it. Those elements are fixed in that order. Like lists, they can hold different data types.
So why? Why would you want something you can't change? Isn't flexibility good?
That's the crucial question. It often boils down to data integrity. You use tuples when you want to ensure that a collection of items doesn't change accidentally. Think of coordinates, like latitude, longitude, or fixed configuration settings. You want them to stay constant.
I see. It's like a guarantee.
Exactly. Plus, there can be minor performance advantages, and importantly, because they're immutable, tuples can be used as keys in dictionaries, which lists can't. We'll get to dictionaries soon.
Okay, that makes sense. Like sealing the data. Protects it.
Precisely. And one more sequence type to mention briefly, range.
Range. I've seen that mainly with loops.
That's its main use case.
Yeah.
It represents an immutable sequence of numbers, but it's efficient. If you say numbers range 5, it doesn't immediately create a list 0, 1, 2, 3, 4 in memory.
Oh.
No, it creates a range object that generates those numbers 0, 1, 2, 3, 4 only when you need them, like when you iterate over it in a for loop.
Ah, so it saves memory, especially for large ranges.
Exactly. Very memory efficient for looping a specific number of times. 3, structured data. Mapping and unique sets. Mapping and set types.
All right, so sequences are all about order. Lists, tuples, ranges. The position matters. But what if the order isn't the main thing? Or what if you absolutely need to ensure every item is unique?
Right, that shifts our focus. We move into different structures. First, the mapping type, which in Python primarily means the dict, or dictionary.
Dictionaries, key value pairs, right?
Exactly, defined with curly braces. They store data not as an ordered sequence, but as pairs. A unique key that maps to a value.
Like a real dictionary .word key maps to definition value.
Perfect analogy. Or a phone book, name key, maps to number, value. The keys must be unique, and they generally need to be immutable types like strings, numbers, or tuples. The values can be anything.
And the source example is person name Bob, age 30.
Yep. Name is a key pointing to the value Bob. Age is a key pointing to 30. Lookups are super fast because you access the value directly using the key. Like person name.
This seems incredibly useful for organizing structured data, like user profiles, config files, anything where you want to look things up by a specific identifier rather than just a position.
Absolutely. Dictionaries are workhorses in Python for structured data.
Okay, so that's mapping. What about ensuring uniqueness?
That brings us to set types. Starting with set also uses curly braces, like dictionaries, but they don't store key value pairs. They just store individual items.
Just the items.
Just the items. And the defining feature, they only store unique items.
Ah.
If you try to add an item that's already in the set, nothing happens. The set remains unchanged. They're also unordered, generally speaking.
So the example, my set 1, 2, 3, 2.
Results in the set 1, 2, 3. The duplicate 2 is automatically discarded.
Okay, that's handy. When would you use that?
Oh, lots of times. Finding all the unique elements from a list, convert it to a set, checking if an item exists in a large collection very quickly. Sets are optimized for that, membership testing. Or performing mathematical set operations, unions, intersections, differences. Sets make those operations really straightforward and efficient.
Right, instead of writing complex loops to compare items.
Exactly. And just like we had lists, mutable, and tuples, immutable.
Let me guess, there's an immutable set.
You got it. Frozen set, same idea. An unordered collection of unique items, but once created, it cannot be changed.
And why use that?
Same reasons as tuples, mostly.
Yeah.
Data integrity, and importantly, because they are immutable and hashable, you can use a frozen set as a key in a dictionary or as an element within another set. 4. Advanced concepts. Binary and absence, binary and none types.
Okay, we've covered a ton of ground. Numbers, truth, ordered sequences, mappings, unique sets. Are there any other major types we should touch on? Maybe more specialized ones?
Yes, definitely a few more, particularly when you get closer to the machine level or deal with the absence of data. Let's talk binary types first.
Binary. Like raw data.
Exactly. First, there's bytes. This represents an immutable sequence of bytes. Think of raw data from a file, an image, a sound file, or data coming over a network. It's not text characters, it's the actual byte values.
Immutable, like tuples and frozen sets.
Right. Then, if you need to modify binary data, you use byte array. It's the mutable counterpart.
Okay, so if I needed to change a few bytes in that image data directly.
Byte array would be the tool. It lets you work with a changeable sequence of bytes, useful for things like building network packets piece by piece or certain kinds of binary file manipulation.
Got it. And there was one more mentioned, memory view. Sounds technical.
It's a bit more advanced, yeah. Memory view provides a way to access the internal data of an object, like a large bytes object, without making a copy.
Ah, efficiency.
Exactly. Imagine you have a huge chunk of binary data in memory. Creating copies to work with small parts of it is wasteful. Memory view gives you a view into that memory buffer directly.
So you can read or even modify parts of the original data without the overhead of copying.
Precisely. It's crucial for high-performance tasks involving large binary data, like in scientific computing, image processing, or networking, where minimizing memory copies is key.
Clever. Okay, so that handles binary data. What about, well, you mentioned the absence of data.
Right. The final built-in type to cover is none type.
None type.
Its only value is none. Capital N-O-N-E. None represents the explicit absence of a value. It's not zero, it's not an empty string, it's not false. It literally means nothing here.
So, like the example result, none.
Yep. That means result doesn't hold a value yet. Or maybe a function finished without producing a specific result to return.
How is that useful? Why not just use, say, 0 or an empty list?
Because none is unambiguous. 0 is a value. An empty list is a container, just empty. None signifies the lack of any value. It's often used as a default value for function arguments or as a placeholder, or to signal that an operation didn't yield a meaningful outcome. It's a really important concept for managing state and optional values cleanly in code. Outro.
Wow. Okay, that was quite the tour. From simple numbers like 10 all the way to none representing nothing.
Yeah, covers a lot of ground.
So bringing it all together, what does this mean for you listening? We've just navigated this whole landscape of Python's built-in types. Simple numbers, text, ordered collections, unordered collections, unique collections, binary data, and even nothing. It really feels like we've taken a deep dive into Python's logic.
And that's the key takeaway, really. Understanding these differences isn't just, trivia. It's practical.
It's choosing the right tool.
Exactly. The data type you choose, int, list, dig, set, maybe even bytes or memory view, directly impact how well your code works.
Efficiency, robustness, clarity.
All of it. Making smart choices about data types is fundamental to writing good, effective Python code. It ensures your solutions aren't just working, but working well.
It really is like a craftsperson knowing their tools, isn't it? Which hammer for which nail.
Good analogy.
Well, thank you for joining us on this deep dive into Python's data types. We really hope it's given you a clearer picture of how Python thinks about information and how you can use that.
Absolutely. And maybe a final thought to leave you with?
Oh.
Next time you encounter any piece of information, could be anything, a number, a name, a shopping list, a complex data set from work, pause for a second. Think about how you might categorize it in these Python terms.
Interesting.
Is the order important? Does it need to be changeable? Should items be unique? Is it representing the absence of something? This deep dive shows that even simple data has a specific identity. And Python is built to recognize and use that identity. So how might thinking more explicitly about data types change how you organize information, not just when you're coding, but maybe even in your everyday life? Something to ponder.